Hello and welcome to the Irmin v2 presentation. In this talk, I'm going to present what Irmin is and some of the new features that we developed over the last year and how you can maybe use them in your project. Then we will dive into some of the internals of Irmin through a real use case running in production and some of the challenges that we faced. Before we start, Irmin is developed at Tarides and is part of the MirageOS project. So MirageOS is a set of operating system libraries that allow you to build unikernels. That means an application and an operating system bundled into one small standalone unikernel that can run on basically any device. But this part is a bit out of scope for this talk, so if you're interested in that aspect, you are very welcome to visit the MirageOS website. So first off, what is Irmin? Irmin is a library built in OCaml that enables you to create versioned key value stores, and it follows the same design principles as Git. So as such, it also has some of the Git features. For instance, you can create branches and merge them. It's also distributed, which means you can have multiple replicas of the same Irmin store on different machines and perhaps with different states, and you can sync them using pull and push operations, just like Git. And it's also developed for MirageOS, which means it builds into small unikernels that don't depend on Unix syscalls, for instance. And since the requirements for unikernels are quite close to the one for web-based applications, that also means Irmin builds to JavaScript. So we have several use cases that use Irmin. First off, internet services. For instance, the DNS server or ARP service of Mirage are built using Irmin as their storage. And Robu also built a CalDAV server using Irmin as a storage. You can also build browser-based applications. For instance, QKeeper is a nice to-do app that runs only in the browser and embeds Irmin as the storage. And it's also very well suited for data-intensive applications. For instance, the Tezos cryptocurrency stores its ledger in an Irmin store. And also, if you are familiar with OPAM packaging and opam-repository, then the CI of opam-repository stores its results in Irmin. So Irmin follows the same principles as Git, but what are they? So the data is basically organized under snapshots, which are called commits. So a commit is a record of the state or the version of a store. And it contains metadata, such as a message commit, a date, an author. It also contains a link to the previous versions of the store, and a link to the tree object. The tree object is what contains the key to value bindings. As in Git, the keys are tree-shaped. That means you can have subtrees in a tree, just like you would have subdirectory in a Git directory. So a tree is basically a list of links to either contents or another subtree. All these components are hashed and references through the hash, which means you have a natural hash counting in Irmin. For instance, if two trees point to the same content, then the content is not duplicated. So three nice features of Irmin. It's compatible with Git, so that means you can open and change the state of a Git repository using Irmin, or the opposite. You can open an Irmin store and use the Git command line to interact with it. All components are customizable. That goes from the contents that are stored in the store, unlike Git that only handles blobs of data and doesn't know about their structure. But you can also customize the hash or the metadata, the branches, basically any part. It's also storage agnostic, which is a great feature. So that means the part of Irmin that handles tree, commits, and contents doesn't need to know how that data will be stored on the disk. And you can plug basically any storage layer to that. So those storage layers, we call them Irmin backends, and we provide a few of them. And the huge benefit of that is, depending on your needs and what your application is, you can have a different storage layer. For instance, if you don't need the data to be persisted to disk, then you can use a simple hash table. That's what's implemented in Irmin-mem. If you want to be compatible with Git, you can use the Irmin Git backend. And if you have very specific needs, then you can write your own backend that is optimized for your use case. So there have been a lot going on for the V2 release, but here I'm going to focus on 3 aspects that is the use of the library. The first one is a simple PBX that avoids a lot of boilerplates when you write an irmin store and makes it really easy to use. The second one is a CLI interface, so now you can interact with your store without writing a single line of OCaml and just using the CLI. And we also now provide a GraphQL interface and server, so you can set up on top of any irmin store a GraphQL server that will serve a GraphQL interface that you can use through the web, maybe from another application, perhaps written in another language or anything. So we will have a short demo of that. We are going to build a very basic GraphQL server that serves an irmin store with structured data. And then we are going to interact with it using GraphQL request and the CLI tool. So here's the piece of code that we are using for the demo. As I said, irmin is highly customizable. That means you can provide custom components for different parts, such as hashes, branches, metadata. But here we are only going to provide a custom user and use the defaults for others. So to provide a custom content, you have to provide a type T. So here to record with two fields, and you have to provide an OCaml value that represents that type, so that irmin knows how to serialize it and hash it. So before the V2 release, you had to do it by hand, and it was quite tedious. But now you can just use the ppx irmin to derive it for you. You also have to provide a merge function that will be used when you merge 2 branches, but I will not dive into the details here, so you can just check out the documentation if you're interested. Then I can create an irmin store from the Git backend on the file system, and it's a key value store using only the contents. I will not use any of the remote features, so I will just set it to none, and I can create a server using the functor provided by irmin-graphql. Then I can create an irmin repository under /tmp/irmin and the GraphQL layer on top of that I will serve using co-HTTP. So now I can run the example. The server is running now, and I can open it in a browser. So I have a nice interface. On the left, I can type requests, and on the right, I will get the results. So here I'm going to create a new key with the value John with age 10, and I will get the hash back. So here we go. And I can also read what's in the store. So if I want to read the key under admin/John, I should get the value I just added. So here we go. And I can also ask for a key that doesn't exist, and in that case I will just get nil. I can also browse the database using the command line interface. So if I go to the directory where the repository is, I can ask irmin to give me the value of admin/John, and I will get the value I just added. And I can also set a new value for Jane, for instance, and recover it. And as I said, irmin is also compatible with Git. That means I can also use the Git command line to read what I just did. So if I check out on master and print what's in the directory, I will get the 2 keys that I created. And of course, irmin is based on commit, so each change that I made created a new commit, so I can go back in time. I can also check that with the git command line by showing git log. And then I will see I have 2 commits, one for adding John and one for adding Jane. Now let's dive into some of the internals of irmin and talk about irmin-pack. So irmin-pack is an irmin backend that we developed part of the V2 release. It was developed specifically for the Tezos use case, which is storing the Tezos ledger. So as a blockchain, it makes the commit very well suited for storing and organizing the data. At the time, Tezos was using an LMDB backend, which used 250 gigabytes on the disk. So our main goal here was to reduce the size of the Tezos storage. Irmin backend must provide a pretty simple interface. Of course, that can hide an arbitrarily complicated implementation, but the basic operation allow adding and looking up. All the data is content addressable, so that means the data can be retrieved based on the hash. We also have other constraints. So because a Tezos node can perform multiple operations at once, such as validating blocks, answering user requests, or getting data from the network, we cannot block, and the latency when performing an operation must be minimal. We have to be disk optimized, so we have to go way under the 250 gigabytes, and we have to grow less than 20 gigabytes per month, which was the growth rate at the time. We also have a hard bounded memory constraint because a Tezos node can run on very small devices such as Raspberry Pis or small VPS. And finally, a Tezos node is composed of 3 processes that should be able to read the storage independently of each other. So we have to provide a single writer, multiple readers access pattern. So an irmin-pack store is made of 3 components. The first component is the pack component. Its role is to store the serialized data that it received into a single file. It's an append-only file, so that means you can only write data at the end of the file and you cannot alter any existing data. It contains a file header for versioning and integrity reasons. And then the data is appended along with the length, so we know how much to read, and the hash for integrity checks. So as we saw, nodes and commits contain links to other objects. So first optimizations that helped us save a lot of space is we made those links as offsets in the pack file instead of hashes. So since offsets are much smaller than hashes and there are a lot of them, we saved a lot of space that way. It's not an issue, of course, because the data is immutable. That means the offset cannot change in the pack file. So we cannot break the leaks. A second optimization consists in deduplicating the path names. So as we saw, the tree contains path to value bindings. So whenever a new tree is written, all the paths have to be written with it. That can lead to a lot of duplicated data. For instance, typically when working on a Git repository for source control, the change of paths do not happen that often because you mostly change the contents of your files instead. But yet you have to rewrite the path name for every commit. So to solve this, we deduplicate the path name by referencing them in another component, the dict. So the dict is basically a bidirectional binding table from path name to identifiers, which are shorters. So whenever we write a node to the pack, we first check if the path was already used in the past, and in that case we use the corresponding ID. And if that's not the case, we use a fresh ID and add it to the dict. We perform the opposite operation when dereferencing, when we need to read a node. In the Tezos use case, the dict is quite small, it's about 10 megabytes, so it's also kept entirely in memory for speed reasons. Okay, so now having that big append-only pack file is convenient when writing, because we just have to append it at the end of the file. But searching in it is obviously not optimized, since we would basically have to read the whole file linearly to find our data. So the third component is responsible of indexing the data. That means it contains bindings from hash to offset and length in the pack. So we extracted that component as a separate library. So on the surface, index is a simple key value table. So you can find and replace value just as in a hash table. But remember, we also have other constraints, such as the multiple readers constraint or the bounded memory. So Tezos has more than 300 million values stored, so we need a specific solution for that. That library is virtually independent from Irmin and available through OPAM, although it was developed specifically to meet the constraints. So in the context of data-intensive applications, the largest source of performance drop is access to the disk, so reads and writes. So our goal here is to provide a single read lookup to ensure good performance. We also need the memory to be bounded, no matter the number of bindings. So for that reason, the index is divided into 2 parts. The log is a write-only file that contains the most recent bindings. It's duplicated in memory with a hash table. And when we need to read, we read it from the memory. And when we need to write, we write both on the disk to be able to recover on a crash or on a reboot. And we also write it in memory. When adding too many bindings, we have to clean the log somehow to ensure that the memory remains bounded. So the log file is bounded with a hard limit that is customizable. So now we can find and we can add value to the log, but what happens when we reach that log size limit? So when that happens, we write the log file into a new file, which we call the data file, and then we clean the log file. We empty it. Each time the log gets full, we merge the log file with the older data file and provide a new data file. So as you can guess, this operation is costly, so it all happens in the background. So we can use a simple atomic rename to ensure concurrent access. So that data file contains older values. It's only on the disk. We don't keep it on memory. And it's a read-only file. Most importantly, it's sorted by the hashes. So that's an environment the merge operation has to keep. So that will allow us fast lookup of the data. So whenever we want to find some data, we first look up in the log in memory. And if we don't find it, we look in the data by performing an interpolation search. So it's similar to a binary search, except it can find the data quicker, provided that the hashes are well distributed, which is the case here. On top of that, we have a fanout that is able to tell us on which page of the disk we can find a specific key. So in the end, we only run the interpolation search on one page of the file, which is done using only one syscall to read. Another tricky aspect is how index integrates to the big picture of irmin-pack. So because flushing is costly, we do not do flush for each write on the disk. And it's okay in the context of Tezos because they can replay and recover the data by other means, by computations. So instead we have bounded memory buffers, which get flushed when they are full. But obviously concurrent readers cannot read those because the memory is not shared. So we still have to flush them somehow for the concurrent readers to see them. But as you know, index contain references from hashes to offset in the pack. That means each read has to go through the index first. So we must ensure that anything written in the index points to a valid offset in the pack. So to do that, we enforce a specific order when flushing to the disk. So whenever index has to be flushed because its buffers are full, we also need a pack to flush its buffers before that. So that way we ensure that anything written to the index was previously flushed to the pack. So the pointers are still valid. So in index, we provide flush callbacks that we use to keep that invariant and ensure integrity. So now we said that performance was our main goal while developing this backend. So what are the results? The Tezos ledger contains about 350 million objects. We managed to reduce the disk space from 250 gigabytes using NMDB down to 25 gigabytes with irmin-pack. And we reduced the growth rate from 20 gigabytes per month to 2 gigabytes per month. We ensure that the memory is bounded and we need less than 1 gigabyte. But this limit is customizable by changing the log size. So if you have a more powerful machine, you can have faster lookups by raising that limit. And we also ensure that the reads that we provide are low latency reads thanks to the single read indexing. So our worst case is under half a second, and a typical data recovery is under 100 milliseconds. That includes finding in the index, reading in the pack, dereferencing the path names with the dict, and then deserializing the data and performing integrity checks. So what's next for Irmin? We are actively working on many interesting features. The layered store will allow you to combine different stores. For instance, you could use an in-memory backend for most accessed values and a persisted backend for other values for performance reasons. Also, we have some improvements on Irmin type. Irmin type is our dynamic type library. It's responsible of serialization, hashing, printing. So we have a lot of nice performance improvement that will speed up Irmin overall. As we saw, we also provide a GraphQL server. We also have an HTTP server on top of Irmin stores, but we also want to provide RPC servers using, for instance, Cap and Photo for performance-focused applications. We're also working on a garbage collection similar to Git.gc to help clean up unreferenced commit trees and contents. And we also want to provide some verified component as part of Irmin to improve the confidence in the software. Thank you for watching this presentation. If you're interested in MirageOS, you can check the website. It contains a ton of resources that you can use to learn what it is and how you can use it. We also have an Irmin website that contains the API documentations, tutorials, and examples. And of course, all the projects that I mentioned are open source and available on GitHub. So we are always happy to welcome new contributors and users, and feedback is always appreciated. Now I guess we will have a bit of time for questions if you have some.